This one might be like the juiciest one. Equilateral triangles, they seem like they're the simplest thing. I mean, geometrically, when you think about what an equilateral triangle is, it's not the world's hardest thing to draw. I mean, if you're doing it as a rough sketch. If you actually had to construct an equilateral triangle, that's a pain. I don't know if you remember constructions from geometry in high school. I mean, I don't even think they require geometry in college. I mean, let's just put it this way. Geometry is such an infrequent course in college that the course doesn't always run. All right? It's not a requirement, and even if it were a requirement, I don't know how many people would take it anyway. So, but having a good foundation in geometry tends to help with a lot of things. Equilateral triangles, you split them in half, you have 30, 60, 90 right triangles. 30, 60, 90 right triangles are one of the foundations of trigonometry. So, I mean, it's just like, it's everywhere. But I'm getting ahead of myself. Let's draw the graph that we're expected to draw. But these equations, I mean, the way they're presented, they're fine, I guess. You can put them in the calculator, but there's a slightly better way to represent them. I'm going to write y because I just don't feel like writing f of x. Negative 1/2 x plus 1, and y would be equal to positive 1/2 x minus a 1. All right, I just cleaned it up a little bit. If you don't pick up on that, that's fine. Put it in your calculator and see what's going on. But I see a variable x and a numerical denominator, which means that we're dealing with a linear function. You don't really need a calculator to plot a linear function. All right, so I'm going to lean over here and draw my perspective graph by hand. You know what? I'm going to do it like that. Ah, crap, I can't draw. Hold on. I'm going to do it with the line draw tool because I just can't. All right, so we have, for the first graph, a y-intercept of 1 and a slope of negative 1/2. I don't know specifically just by looking at it where that's going to end up, but at least I can plot the y equals 1. For the second equation, I have a y equals negative 1, so I'll plot that. Now, you have two lines that have differing slopes. That means they're going to intersect at some point. Now, I could jump the gun and go to the calculator and do things like that, but if you know that they're going to intersect, they're linear functions, so it shouldn't be too bad to actually come up with the intersection algebraically. So I'll just do a quick negative 1/2 x plus 1 and set it equal to positive 1/2 x minus 1. All right, so if I subtract 1/2 from both sides, I'll just move the x's to the left. I'm going to get negative x. And then subtract the 1 from both sides, I'm going to get a negative 2. And so I get x equals 2. All right. Since it's an intersection, I just need one of the equations. So I'll take the second one, pop in the 2. And it turns out you get 0. All right, so they're going to intersect at 2, 0. Now this is actually a fair amount of unnecessary work, but really only for this situation. The reason I'm saying that is because if I had put this in the calculator, I would have seen that the intersection points between the two graphs is at 2, 0, whether I looked at the graph or if I looked at the table. But as you know, you can't always rely on the convenience that happens sometimes in an example that's presented in class. You know, it's like, oh, well, it worked out beautifully when you went over in class, but then when I got the one on the test, it was like disgusting, right? So you need an approach that's going to work in all cases, right? So that's why I show you things like solver, intersect function, and stuff like that, all right? So this is just the algebra behind the intersect function. And honestly, full disclosure, the only reason I did it algebraically is because I didn't feel like walking over there to get my calculator and do it on the solver. Like, it's like right there, but I didn't want to, because I had just come over here and I felt like, man, I was just there. I could have grabbed it while I was there, but I didn't, and I would have felt foolish. I don't know that you would have noticed, but I would have noticed, and that's what matters. All right, so at 2, 0, I'm going to have that intersection. So I know I have a point here. All right, so I'm just going to read the question again. The base of solid, oh, actually, I don't think I ever read the question. The base of solid S is the region enclosed by the graphs, and x equals 0. All right, x equals 0 is the y-axis. So we're talking about a triangular region. Cross sections perpendicular to the x-axis are equilateral triangles. All right, so I'm going to draw that triangular region. So there's like a lot of triangular stuff going on in this. All right, so this is the base of that solid. It's crazy. I'll label x and y. Give it a little bit more detail. All right. So emerging from this are equilateral triangles, infinitely many of them. All right, so this is going to be like some triangular wedge kind of thing. All right, so I'm going to go purple for those keeping score at home. Get rid of that extra schmutz there. I can't get rid of the schmutz. Stuck with the schmutz. Hold on, undo. Undoing. Oof, look at that. All right. I mean, as schmutz goes, there isn't much there, so that's fine. I can live with that. All right. So I have to create an equilateral triangle out of this. That's somehow jutting out of the paper. So again, another perspective drawing. But this one, I mean, I made my way through the square one pretty well, I thought. The semicircular one, not as good. This one's going to be an utter disaster. It's not going to be pretty. So let me just sit down, brace myself here. It's going to be pretty disgusting. All right. All right, I'm going to take it from the midpoint of the base and then shoot up. Sounded wrong. All right. And I completely missed at the top, so nice teacher strategy for handling stuff like that. Just make the point bigger. There we go. Look at that. I'm going to shade in the face of it so that I don't go cross-eyed when I'm looking at it. No offense to anybody who might be cross-eyed. All right, I know it doesn't look equilateral, but I warned you in advance anyway. But my excuse is that it's supposed to be a perspective drawing anyway. So just change your perspective and pretend I'm a good drawer or artist, whatever. All right, so, oh man, that's brutal. Oh. I don't know, I'll give it a border or something, I don't know. I think the black border just made it worse. Undo. How about a red border? I don't know. put the altitude in there. I'll do that again. All right, it's just getting worse, but I'll zoom out a lot so it doesn't look as terrible from a distance, like a masterpiece at a museum, because that's what that is. All right, so that's the best I can do. So obviously the best you can do is going to be good enough for me, as long as you attempt it, because I will ask you to draw on the test minimum one cross section. I mean, if you want to put like 30 cross sections in, by all means, but I mean, I barely got through one, so I mean, whatever you can do. All right. But what we need to do here again, and that doesn't even look the right angle. Yeah, that's brutal. Let me just check something here. Nah, that didn't help. All right, just made it worse. All right, so what I need is the area of one face of this triangle. And once I have that, I'm going to integrate it over the interval. Right? By finding the intersection, we know that the interval extends from 0 to 2. So I'll pop that in here, 0 to 2. I just need the area of that triangle. All right, so we'll start with the area of a triangle formula. You think, well, that's as simple as it gets, right? Area of a triangle. Half the base times the height. Now you think back to the square and the semicircle. Once we found the base, we pretty much found the height. With the semicircle, the base was the diameter. So that made the height the radius. You just chop the diameter in half. So that was good. For the square, whatever the base was, that was equal to the height. So that was good. Here, well, no, that's not how it works. All right, so what we have to do is figure out what the height is going to be given our knowledge of this situation. All right, so I know a couple of things. I know the distance from here to here, this distance here, is some value y. All right, because it's going from the x-axis to a point in space. All right, but it happens to fall on this line. All right, which is the equation -1/2 x plus 1. All right. So that means I put my right angle at the wrong place. The picture still looks terrible. So I like the situation improved. All right, so we have an equilateral triangle. The altitude splits the base in half. All right, so what that means is that I now have 1/2 the base. I already have that. That's good. I just need the height. All right, but that was the challenge to begin with. All right, so what we're going to do is off on the side here, we're going to invent a rule. Area of a 30, 60, 90 right triangle. All right, so let's draw a 30, 60, 90 right triangle. Well, we'll start with the equilateral triangle and chop it in half. All right, so we're working with y's here, so that's what I'm going to use. This is a formula or a procedure that you might know from trigonometry. if you define half of the distance of the base as one variable, we'll call it y, the hypotenuse is going to be double that, right? Because it's half of one side. The hypotenuse is equivalent to that one side, right? At this point, if you happen to know what the altitude is going to be, you're good. But if not, you just solve for it. So I'll call that h. Pretend I don't know it. H squared plus y squared would be equal to 2y squared. I put my parentheses in the wrong place. Because, you know, why not? All right, so solving for h, I get h squared is equal to 3y squared. Taking the square root gives me h equals y times the square root of 3. All right, so that's my height. All right, so if I want the area of this triangle, which again is half the base times the height, based off this information, I already know half the base, that's y. We just discovered that the height is y radical 3. That's this guy here. An area of an equilateral triangle would be y squared radical 3. Based off of that definition. So we have a nice formula here. Because I know what y is. It's right here. I also have another y if I want to. I could use the 1/2 x minus 1. That's an equivalent y. It's the same distance. All right. So in this case, I'd be looking at an area equal to negative 1/2 x plus 1 squared radical 3. If I want the volume of one slice, I take that and slap a dx on it. Almost said dy. That would give me the volume of a single triangular slice, right? Because again, we have to assume that there's some thickness. I'm going to zoom in real quick, but then I'll bring it back out. We assume that the thickness is still there. We have this thickness in the x direction. That thickness is dx. All right, so that gives you a volume of a single slice. All right, so if I want the volume of all slices integrated together, well, that's exactly what I do. I integrate on the interval of 0 to 2. That expression. I could move some things around, but I really don't need to. I'll just write it exactly as is because it's going in the calculator anyway if I actually need the volume. Now it says find the volume, so I suppose we have to do it. So I guess I'm going to change my mind immediately and just put the radical 3 in front. All right. So let me make the long journey over to my calculator. I found out earlier today that I do in fact have to hit record if I want to make a recording. So, video. Nice glare, nice distracting glare for everybody. Come on, you son of a gun. There's no way around it, the lights have to go off again. Yep, that's the one. Okay. but apparently this is the feature that, like, if I wanted to put my face in a video, this is like when people on YouTube do that, that's what they do, but I don't want people to see my face. Bad enough they comment on my math knowledge. Like, dude, your head's shiny. I'm like, shut up. Cool. All right, yeah, so as I was saying, it's on the interval of 0 to 2, radical 3 in front, math 9, negative 0.5x plus 1 squared dx. And so you get this value, 1.155-ish, and that ought to do it. And so, yeah, and then tuck it in the corner. All right. I might finally learn how to use this app. The craziest thing is I've been using this app for 3 years now. And these are not new features. I'm only learning how to use them now, though. So, in terms of technique, I mean, the little bit of a twist here is the new formula for area of a 30, 60, 90 right triangle. And actually, it's not even the area of the 30, 60, 90 right triangle. That's sort of a misnomer. I don't know why I even wrote that. We're using 30, 60, 90 right triangles and their rules to help us figure out the area. Oh, hello. We're using that information to find the area of an equilateral triangle. So it's still 30, 60, 90, just not, that's not ultimately what we're looking for. Catch the mistakes before the internet does. Equilateral. Yeah. Anyway. So what this means for us is you could use this rule instead of doing all this work. I wouldn't want to do all this work. I didn't want to do all this work. Just now. I did not at all. Right? That y value in this formula, that's actually your, oh really it's the length of a side, right? A single side, or a half side. So if you know the value of the side of an equilateral triangle, then now all you have to do is chop it in half, you get that, square it and slap on a radical 3. Right, so that's not bad. And in fact, you could even write a program in your calculator. I mean, some people are like, yeah, I'll write a program with that formula in it. I'm like, no, write a program that'll actually make the formula do math for you. That's kind of the purpose behind programs, because it's really just a matter of inputs and outputs. Right? So if you just say, what's the side, chop it in half, store it in as y, store it in as x, store it in as q, it doesn't matter, s if you want, and then run the program, then it'll spit out a numerical value. It's not going to do the calculus for you, but at least you'll have something. Maybe a little later I'll do that for you. I'll show you how to do it if you don't already know. Because I know people, they know how to use the program function to cheat. Like, oh, you got to memorize these formulas. Like, yeah, I'll memorize them, all right. I'll memorize them right here. Program, edit, and then you start typing them in. All right, that'll make you clear your calculators. I'm a firm believer that these calculators are resources, especially since you had to pay for them, right, assuming you paid for them. So you paid for them, so learn how to use them. And so if I have time at the end, I'll show you how to do it. If not, I'll make a video. It'll be like my most liked video. The ones where I show like real math nobody cares about. Thumbs down, you suck. But then I show something like, here's how you write a program in your calculator to help you memorize formulas. And you're like, yeah, thumbs up. Yeah. So anyway, this next problem is pretty much the same thing. So I think this is one of those situations where you're probably best served to try it on your own and look to the answer key online to see where you are. All right.